We continue with Einstein theory and time and space, which is as one unit, and I explain it in Arabic because I understood it, and I hope it will be clear. And it is very nice. The quality of this video is very good, and how he explain it, it's very good, because apparently Einstein, he think of the speed, the motion, the time, the space, and the gravity. So if we move through space with high speed, the time gets short. But if our speed is less, like somebody on the platform and walking, then the time it will be longer. So if I leave my identical twin on the platform, and then I ride in high speed, like the speed of light, so I will cross. Speed of light is 300,000 kilometers per second. So I could go 300,000 kilometers in 1 second. And if the person on the platform walk this distance, it will take years. It's not only his generation, but many generations after him. If he has long legs and he will do one step, in each one step, or he walk 5 kilometers per hour, which is 5,000 kilometers per hour. So you could make the mathematics and how many thousands of years it takes him to finish the space if the speed is low. And that's why the speed or the motion, speed of motion, the time and space are 3 dimensions, and the 4th dimension is the gravity. How these big stars or big galaxies, how they impinge on time, the time and space curved around it, and that's why these will continue to move in the universe. It's very interesting. So we'll continue. And this is really my education, and I'm listening, so at the same time I could understand it more, I could explain. Even a few people who get benefit, it is better than nothing. Although this morning so many subscribers withdrew from the channel. It's up to them, they are free. Because it is difficult, so it is better for them is to choose the easy way. This is the new generation, easy way, not the hard way.
He helped start, but never accepted. Part 3. The Great Quantum Debate: Determinism, Causality, and Reality. Einstein's relationship with quantum mechanics embodies one of science's greatest ironies. He pioneered quantum theory in 1905 by explaining how light behaves as discrete packets of energy called quanta, not continuous waves. This work earned his Nobel Prize. Yet Einstein spent the last 3 decades of his life arguing that quantum mechanics, as developed by Niels Bohr, Werner Heisenberg, and others, could not be the final truth about nature. His objections were not mathematical, but deeply philosophical.
He did not understand the quantum
debate,
physics.
We must grasp what quantum mechanics says about reality. Classical physics, including Einstein's relativity, assumes the world has definite properties independent of observation. A particle has a specific position and velocity at every moment, whether or not anyone measures it. Measurement reveals pre-existing properties. Quantum mechanics shatters this assumption. According to the Copenhagen interpretation, developed primarily by Bohr and Heisenberg, particles do not have definite properties until measured. Before measurement, a particle exists in a superposition, a combination of multiple possible states simultaneously. The particle is not secretly in one definite state that we simply do not know. It genuinely exists in multiple states at once. Measurement forces the particle to collapse into one definite state. Which state appears is fundamentally random, governed only by probabilities that the theory calculates precisely. But nothing determines which particular outcome occurs in any individual measurement. God plays dice, in quantum mechanics' view. Einstein found this philosophically unacceptable. His objections crystallized in a famous 1935 paper written with Boris Podolsky and Nathan Rosen, known as the EPR paper after their initials. The paper presented a thought experiment, later refined by physicist David Bohm, that Einstein believed exposed quantum mechanics' incompleteness. Imagine two particles interact and then separate, flying off in opposite directions. Quantum mechanics describes them as entangled, meaning their properties remain correlated even across vast distances. Measuring one particle's spin, which is a quantum property similar to rotation, instantly determines the other particle's spin, even if the particles are light years apart. If you measure the first particle and find its spin pointing up, the second particle's spin must point down. The Copenhagen interpretation says the first particle had no definite spin before measurement. It existed in a superposition of up and down simultaneously. Measurement collapsed it to one state. Somehow, this instantaneously affected the distant second particle, collapsing it to the opposite state. This seems to violate relativity's prohibition against faster-than-light influences. Einstein argued that a more reasonable explanation exists. Perhaps both particles had definite spins from the moment they separated. Measuring the first particle simply reveals information that was already determined. No mysterious, instantaneous influence crosses space. The correlations arise from common past causes, not spooky action at a distance, as Einstein mockingly called quantum entanglement.
Spooky.
This view requires hidden variables, additional properties beyond what quantum mechanics describes, which determine measurement outcomes. Quantum mechanics gives only probabilities because it is incomplete, lacking these hidden variables. A future, more complete theory would be deterministic, Einstein believed, restoring certainty and eliminating randomness.
At my age, I know a special toy when I see one. I bought this robot puppy thinking it would last a week. That was 6 months ago.
The EPR argument seemed powerful. But in 1964, physicist John Bell proved a remarkable theorem that transformed the debate. Bell showed that any theory using local hidden variables, meaning hidden properties that do not involve faster-than-light influences, must satisfy certain mathematical inequalities. Quantum mechanics violates these Bell inequalities. This meant the question could be settled experimentally. Perform the right measurements on entangled particles and see whether the results satisfy Bell's inequalities or violate them as quantum mechanics predicts. Starting in the 1970s, physicists performed increasingly sophisticated tests. The results consistently violated Bell's inequalities, supporting quantum mechanics. These experiments won the 2022 Nobel Prize and have profound philosophical implications. They prove that Einstein's preferred picture, with particles having definite properties determined by local hidden variables, cannot be correct. Nature genuinely exhibits non-local correlations. Measuring one particle instantaneously affects its distant entangled partner. However, this does not vindicate the Copenhagen interpretation entirely. Bell's theorem shows that any theory matching quantum mechanics predictions must be either non-local, involving faster-than-light correlations, or non-realistic, meaning particles lack definite properties before measurement, or both. Physicists and philosophers disagree about which horn of this dilemma to accept. Some interpretations preserve determinism by accepting non-locality. Bohm developed a hidden variable theory where particles have definite positions at all times, guided by a quantum pilot wave that propagates instantaneously across space. Bohm's theory reproduces all quantum predictions while maintaining Einstein's realism and determinism. But it pays the price of non-locality, violating Einstein's other core principle that no influences travel faster than light. Other interpretations embrace indeterminism while preserving locality. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, every measurement splits reality into multiple parallel universes, each realizing one possible outcome. In one universe, you measure spin up. In another universe, an identical copy of you measures spin down. Both outcomes occur, just in different branches of reality. This interpretation strikes many people as wildly extravagant, multiplying universes to avoid randomness. But it takes quantum mechanics mathematics completely seriously, without adding collapse postulates or hidden variables. Physicist David Deutsch argues it is the simplest interpretation, despite seeming complex, because it requires fewer assumptions. A third approach, called cubism, treats quantum mechanics as describing our knowledge or beliefs about measurement outcomes rather than describing reality itself. From this perspective, the wave function represents subjective information, and collapse reflects updating our knowledge, not a physical process. Different observers can assign different wave functions to the same system, based on their different information. Einstein would have rejected all these interpretations. Bohm's theory, while deterministic, uses non-locality that Einstein found unacceptable. Many worlds multiplies realities unnecessarily and is unfalsifiable. Cubism denies objective reality by making quantum mechanics subjective. None satisfies Einstein's core principles: realism, locality, determinism, and objectivity.
Around the world, children's lives are being torn apart by war.
The deeper philosophical issue concerns what scientific theories should explain. Einstein believed fundamental theories should describe reality as it is, independent of observers and measurements. Quantum mechanics, in most interpretations, refers essentially to measurements and observers. The theory tells us what happens when we measure, but says little about what exists when nobody looks. Einstein found this instrumentalist approach, which treats theories as mere prediction tools without describing reality, philosophically impoverished. He insisted physics should be about nature itself, not just human interactions with nature. As he famously asked Bohr during their debates, "Do you really believe the moon exists only when you look at it?" Bohr responded that the question misunderstands quantum mechanics. We cannot meaningfully discuss reality independent of measurement because measurement and measured system form an inseparable whole. Classical concepts like position and momentum, which we use to describe nature, only make sense within specific experimental contexts. Asking about reality in itself, apart from any possible measurement, asks a meaningless question, according to Bohr. This complementarity principle, Bohr's philosophical framework, says that complete description requires multiple, seemingly contradictory perspectives. Light behaves as waves in some experiments, as particles in others. These are not opposing properties of light itself, but complementary ways humans can investigate light using different experimental arrangements. Which aspect manifests depends on our measurement choice. Einstein never accepted this. He believed Bohr was abandoning the goal of objective knowledge and replacing it with pragmatic description of human experience. Physics was becoming phenomenology, the study of appearances rather than ontology, the study of what exists. Einstein saw this as intellectual defeat, accepting limitations on human knowledge rather than pushing toward deeper understanding. Modern philosophers of physics remain divided. Some argue that Einstein's realist principles are outdated metaphysical prejudices. Science should describe observable phenomena and make accurate predictions. Whether unobservable reality really exists with definite properties is a pseudo-question beyond science's scope. This view, called scientific anti-realism, has respectable pedigree dating to philosophers like Ernst Mach, who influenced young Einstein before Einstein later rejected this position. Others defend Einstein's realism. They argue that science's success depends on approximately true descriptions of unobservable reality. Atoms, electrons, quarks, and quantum fields are not mere calculational devices. They are real entities whose properties cause observable phenomena. A theory that refuses to describe reality beyond observations abandons explanatory depth for predictive accuracy alone. The debate extends to quantum mechanics' practical applications. Quantum computers harness superposition to perform calculations impossible for classical computers. Quantum cryptography uses entanglement to guarantee secure communication. These technologies work spectacularly, regardless of interpretational disputes. Does this prove that questioning quantum mechanics' foundations is pointless philosophy? Einstein would say no. Practical success does not prove theoretical completeness. Newtonian mechanics worked brilliantly for centuries before relativity revealed its limitations. Similarly, quantum mechanics might be a highly accurate approximation to some deeper theory that restores determinism and realism. Without pursuing foundational questions, we might never discover that deeper theory. Indeed, recent experimental advances are revealing new puzzles. Quantum gravity research suggests that space-time itself might be emergent from more fundamental quantum information structures. Black hole physics reveals deep connections between quantum mechanics, thermodynamics, and gravity that nobody fully understands. These frontiers might ultimately require the kind of complete theory Einstein sought. One contemporary debate concerns the measurement problem, which quantum mechanics has never fully solved. Why and how does the wave function collapse during measurement? The theory says collapse happens but does not explain it. Various interpretations offer different answers, from many worlds' denial that collapse occurs to spontaneous collapse theories that add new physics to quantum mechanics. Einstein identified this problem early, calling measurement's special role in the theory artificial and unsatisfying. Another unresolved issue concerns quantum mechanics' relationship with time. Standard quantum mechanics treats time as an external parameter, not a quantum observable like position or momentum. This creates tensions with general relativity, where time is part of space-time geometry and observers moving at different velocities experience time differently. Combining quantum mechanics with relativistic time remains an open problem that might require reconceptualizing both theories.
You always wondered why that app didn't exist. Now you can make it. Meet Replit Agent.
Einstein's critique also highlighted quantum mechanics' indeterminism as a fundamental flaw. Modern philosophers distinguish between ontological and epistemic indeterminism. Ontological indeterminism means the future is genuinely open, not determined by the present. Epistemic indeterminism means we cannot predict the future because of knowledge limitations. Classical chaos theory exhibits epistemic indeterminism, systems so sensitive to initial conditions that tiny uncertainties explode into complete unpredictability, but remain ontologically deterministic. Quantum mechanics seems to involve ontological indeterminism. Measurement outcomes are not simply unknown, they are fundamentally indeterminate until measurement occurs. Einstein believed this threatened causality and rationality. If events occur without sufficient causes, how can we understand nature through reason? Defenders of quantum indeterminism respond that Einstein confused determinism with comprehensibility. Nature can be rationally understandable and mathematically describable while remaining indeterministic. Quantum mechanics provides perfect probabilistic predictions. Perhaps this represents the deepest level of understanding nature permits. This raises the question, what makes an explanation satisfying? Einstein wanted deterministic explanations that showed necessity. Given these causes, these effects must follow. Quantum mechanics offers probabilistic explanations. Given these conditions, these outcomes occur with these probabilities. Is probabilistic explanation genuinely explanatory or merely descriptive? Philosophers remain divided. Some argue that probabilistic causation is perfectly legitimate. Many everyday explanations use probabilities. Smoking causes cancer probabilistically, not deterministically. Others maintain that probabilistic explanations are incomplete and should ultimately reduce to deterministic mechanisms, even if unknown. Einstein's position also reflected his scientific practice. His greatest discoveries came from seeking unified, deterministic explanations. This methodology succeeded brilliantly for relativity. But quantum mechanics seemed to require abandoning this approach. Perhaps Einstein's methodology, while extraordinarily fruitful in some domains, was unsuited to quantum phenomena. The stakes extend beyond physics. If quantum indeterminism is fundamental, it might provide room for free will in an otherwise deterministic universe. Some philosophers and neuroscientists argue that quantum randomness in brain processes could enable genuine choices not determined by prior causes. Others respond that random quantum events hardly constitute meaningful free will, which seems to require control and rationality, not mere indeterminism. Einstein himself did not believe indeterminism rescued free will. He was a compatibilist about free will, holding that freedom and determinism are compatible. We will explore this in Part 8. But his rejection of quantum indeterminism did not stem from worries about free will. It stemmed from his conviction that fundamental physics should describe a rational, comprehensible reality. The quantum debate also reveals tensions between mathematical beauty and empirical adequacy. Quantum mechanics' mathematical structure is extraordinarily elegant. Its predictions have been verified to staggering precision. Yet its conceptual foundations remain murky and disputed nearly a century after its development. Should we accept this situation, or demand both mathematical elegance and conceptual clarity, as Einstein insisted? Contemporary physics faces similar tensions in string theory and quantum gravity research. These theories exhibit beautiful mathematics, but lack experimental evidence. Critics argue they repeat quantum mechanics' mistake, prioritizing mathematical formalism over clear physical interpretation. Defenders respond that Einstein himself used mathematical beauty to discover relativity before experiments confirmed it. Einstein's quantum legacy thus remains ambiguous. He was wrong about hidden variables, wrong about quantum mechanics being incomplete in the way he thought, wrong about determinism being restorable without abandoning locality. But he was right that quantum mechanics raises deep conceptual problems. He was right that physics should aspire to objective description of reality. He was right that foundational questions matter, not just practical applications. Perhaps most importantly, Einstein demonstrated how philosophical principles can guide scientific investigation. His objections to quantum mechanics were not obscurantist resistance to new ideas. They were principled arguments based on carefully articulated criteria for acceptable theories. Even when wrong, his arguments clarified what was at stake and pushed the field toward deeper understanding.
I thought switching broadband was going to take ages and be really problematic.
The experimental tests of Bell's theorem would never have happened without Einstein's EPR thought experiment provoking them. The quantum debate continues to evolve. New interpretations emerge regularly. Experimental techniques allow testing scenarios that were once pure philosophy. Quantum information theory has transformed how physicists think about quantum mechanics, emphasizing information and correlations over particles and waves. These developments might eventually lead to the conceptual clarity Einstein sought, or they might show that quantum weirdness is simply how nature is at the fundamental level. Part 4. Einstein's God, Religion, Spinoza, and Cosmic Religion. Einstein's religious views were complex, subtle, and widely misunderstood during his lifetime and after. He rejected traditional religious belief in a personal God who answers prayers, rewards virtue, or intervenes in natural processes. Yet he spoke frequently about God, causing confusion among both believers who claimed him and atheists who dismissed him. Understanding Einstein's conception of God requires examining his intellectual relationship with the 17th century philosopher Baruch Spinoza. Spinoza, a Jewish-Dutch philosopher, developed a radical reinterpretation of God. Traditional theology distinguishes God from nature. God is a supernatural being who created the universe and can miraculously intervene in natural law. Spinoza collapsed this distinction entirely. For him, God and nature are identical. There is no supernatural realm separate from the natural world. Spinoza's God is not a conscious person with desires, emotions, or purposes. Rather, God is the totality of nature itself, operating according to eternal rational laws. Everything that exists is part of God, and everything follows necessarily from God's nature, just as mathematical theorems follow necessarily from axioms. Free will, miracles, and divine punishment are illusions arising from our incomplete understanding. This pantheistic view, equating God with nature, was condemned as atheism in Spinoza's time. Spinoza was excommunicated from the Jewish community, and his works were banned by Catholic and Protestant authorities. But his philosophy profoundly influenced the Enlightenment and later thinkers, including Einstein. Einstein discovered Spinoza's writings as a young man and found in them a philosophical worldview that matched his scientific intuitions. He repeatedly declared himself religious in Spinoza's sense. When asked if he believed in God, Einstein responded, "I believe in Spinoza's God, who reveals himself in the lawful harmony of all that exists, not in a God who concerns himself with the fate and actions of human beings." This Spinozistic religion manifests as Einstein's cosmic religious feeling, which he described as the most profound emotion we can experience. It is the knowledge that something impenetrable, both beautiful and terrible, exists beyond our limited understanding. Contemplating the universe's rational structure, its mathematical elegance, and its comprehensibility to human reason fills Einstein with awe and reverence. This emotional response to cosmic order constituted his religiosity. For Einstein, scientific investigation was religious worship. Discovering nature's laws meant revealing God's structure. The fact that the universe follows comprehensible mathematical principles seemed miraculous. Why should human reason, which evolved for survival on African savannas, be capable of understanding quantum mechanics or general relativity? Einstein called this the eternal mystery, the comprehensibility of the universe. This comprehensibility suggested to Einstein that the universe embodies rationality at its core. Nature is not arbitrary or chaotic. It follows elegant mathematical laws that human minds can discover through reason. This cosmic rationality was Einstein's God. Unlike traditional theology's personal deity, Einstein's God does not love, judge, or intervene. It simply exists as the rational structure of reality. Einstein explicitly rejected anthropomorphic conceptions of God. He found the idea of a God who rewards and punishes, feels jealousy or wrath, or cares about human behavior childish and primitive. Such beliefs project human qualities onto the cosmos. They arise from fear and desire for comfort, not from genuine understanding. This put Einstein at odds with organized religion. Traditional Judaism, Christianity, and Islam all posit a personal God who relates to humanity, hears prayers, and expects moral behavior. Einstein considered these conceptions primitive superstitions, though he expressed this view more diplomatically in public. He wrote privately, "The word God is for me nothing but the expression and product of human weaknesses. The Bible a collection of venerable but still rather primitive legends." Yet Einstein did not consider himself an atheist. He distinguished between rejecting anthropomorphic religion and rejecting cosmic religiosity altogether. Atheism, in his view, focused too much on what one does not believe, rather than on the positive emotional and intellectual response to the universe's structure. Einstein described his position as agnosticism, tempered with Spinozistic pantheism. His religious views caused constant public controversy. Religious leaders criticized him for denying God's personality and providence. Atheists criticized him for using religious language at all. During a 1929 interview, when asked if he believed in God, Einstein replied, "I believe in Spinoza's God." This statement was widely misunderstood as endorsing traditional theism. Einstein received numerous letters from religious believers asking him to clarify his views. To one correspondent he wrote, "I do not believe in a personal God, and I have never denied this, but have expressed it clearly." He continued, "If something is in me which can be called religious, then it is the unbounded admiration for the structure of the world, so far as our science can reveal it." The tension between Einstein's cosmic religiosity and traditional religion reflects deeper philosophical questions about religion's nature and function. Traditional religion provides comfort, moral guidance, community, ritual, and answers to existential questions like why suffering exists and what happens after death. Einstein's Spinozistic religion offers none of these things. It provides only intellectual and aesthetic satisfaction in understanding nature. Critics argue that Einstein's cosmic religion is not truly religion at all, merely science wrapped in religious language. Religion inherently involves relationship with the divine, worship, prayer, and faith beyond reason. Einstein's position strips away everything distinctive about religion, leaving only wonder at nature. Why call this religion rather than simply philosophical naturalism? Defenders respond that Einstein captured something essential about religious experience, the sense of encountering something immeasurably greater than ourselves, something that evokes awe and humility. Traditional religion anthropomorphizes this experience, projecting human qualities onto the transcendent. Einstein's cosmic religion preserves the core experience while eliminating primitive anthropomorphism. Einstein himself argued that cosmic religiosity represents religion's most mature form. He traced religious evolution through 3 stages. First, fear-based religion arises from terror of natural forces and desire for protection. Primitive peoples worship storms, fertility, and death as gods. Second, moral religion emerges when people conceive God as lawgiver and judge who rewards virtue and punishes vice. This stage includes traditional Judaism, Christianity, and Islam. Third, cosmic religion transcends fear and morality to embrace pure wonder at existence itself. According to Einstein, humanity needs to progress beyond moral religion to cosmic religion. Moral religion breeds dangerous fanaticism because believers think they know God's will and can impose it on others. Religious wars, inquisitions, and persecution result from moral religion's confidence that God takes sides in human disputes. Cosmic religion eliminates such dangers because it locates the divine in nature's impersonal laws, not in human affairs.
Think you've seen everything in your city? Yeah, I did too, until I started using this app.
I've lived in New York for years, and somehow I have never heard of the Louis Armstrong House Museum.
It's literally his real house in Queens. Everything's original. Kitchen, music room, tour recordings, even his voice.
I only found it because I started using Bloomberg Connect.
This app helps you find smaller museums, special collections, and local spots normal travel sites skip, like the Bronze Museum. I went right to the most talked about exhibit because the guide gave me all the context. I didn't stand around wondering what I was looking at. I actually left feeling like I learned something. It's free, no account, no ads, just real culture. And now I've got my next 5 weekend plans lined up. Download the app and find the coolest places you didn't even know existed.
After raising 3 kids and 8 grandchildren, I've never seen a toy create this much genuine happiness. I've been a grandmother for 15 years, and this is the smartest purchase I've ever made. Last month, I got my granddaughter Emma this smart robotic puppy called Wuffy. I still can't believe what this tiny guy can do. This isn't just some stuffed animal. Wuffy has smart technology inside that recognizes Emma's voice and responds to her. He sits on command, barks when you talk to him, walks around the house, even tilts his head and wags his tail exactly like a real puppy. The first time Emma saw him, her eyes lit up. She cuddled him and didn't want to put him down. I could tell she felt calmer and happier than ever. She sleeps better now and smiles more than ever. Wuffy comes in 2 gorgeous colours, white and brown. I picked brown because it reminded me of my childhood pup. What I love most is watching Emma with him. When she pets his head, his tail wags and he makes these sweet puppy sounds back. It's like having a real puppy, but made from completely safe materials. 3 neighbours have already asked where we adopted him from. That's how realistic he looks. Emma treats Wuffy like her best friend. She reads him stories, takes him for walks around the house, even tucks him into bed at night. She's learning love and responsibility. Emma hasn't asked for a real dog since. I have to admit, I got one for myself too. Living alone can feel a bit lonely sometimes, and Wuffy keeps me company. At 50% off, Wuffy delivers all that wonderful companionship for under $30. No feeding schedules, no destroyed furniture, no vet bills or chaos. Right now, you can grab Wuffy for 50% off, but only 47 left at this price. Don't wait until tomorrow when it's back to full price. Order now while the 50% discount lasts and watch your little one's world light up with Wuffy.
This evolutionary view of religion has been criticized as culturally arrogant. Einstein essentially claimed that his philosophical position represents humanity's religious maturity, while traditional believers remain primitive. Critics point out that this dismisses billions of people's genuine religious experiences as childish. It also ignores religion's social and psychological functions, focusing only on cognitive content. Moreover, Einstein's cosmic religion faces philosophical problems. If God equals nature, and nature operates deterministically according to physical law, then everything that happens, including evil and suffering, occurs necessarily as part of God. This makes God responsible for everything, both good and bad. Traditional theology addresses this problem of evil by giving God purposes and humans free will, so that suffering results from creaturely freedom or serves divine purposes. Einstein's God has no purposes, and humans have no freedom. Evil becomes simply part of nature's necessary unfolding, which seems morally inadequate. Einstein acknowledged this difficulty, but offered no solution. He wrote about the agonizing problem of evil and confessed he found no satisfactory answer. Some suffering serves evolutionary purposes, strengthening species through natural selection. But much suffering seems pointless and excessive. If the universe embodies perfect rationality, why does it contain so much apparent irrationality in the form of waste, cruelty, and pain? Traditional theodicy, which means justifying God's goodness despite evil, relies on free will or inscrutable divine purposes. Einstein rejected both options. He denied libertarian free will, which we will discuss further in Part 8. And he rejected appeals to mysterious divine purposes as intellectual dishonesty. This left the problem of evil unresolved, within his worldview. Another challenge concerns cosmic religion's motivational power. Traditional religion motivates moral behavior through promises of reward and threats of punishment, or through relationship with a loving God who commands virtue. Einstein's cosmic religion offers no such motivation. Why should contemplating nature's mathematical elegance make someone behave ethically? Einstein believed that cosmic religious feeling naturally produces ethical behavior because it diminishes selfish ego and cultivates humility. Recognizing our tiny place in the vast cosmos makes personal desires seem petty. We identify with the whole rather than fixating on narrow self-interest. This generates compassion and moral concern. Critics remain unconvinced. Many scientists experience cosmic wonder without becoming especially ethical. Many traditional believers act morally without cosmic religiosity. The connection Einstein drew between contemplating nature and ethical behavior seems contingent rather than necessary. Einstein's religious views also influenced his approach to Zionism and Judaism. Though not religiously observant, Einstein identified culturally and ethically with Judaism. He supported the Zionist project of establishing a Jewish homeland in Palestine. But he opposed Jewish religious nationalism and worried that the state of Israel would become theocratic. He advocated for Arab-Jewish cooperation and a binational state rather than exclusively Jewish sovereignty. His vision reflected his broader religious philosophy, emphasizing universal human values and rational cosmopolitanism over tribal allegiances and religious particularism. Einstein saw Judaism's value in its ethical teachings and intellectual traditions, not in claims to divine election or sacred land. The contemporary relevance of Einstein's religious views appears in ongoing debates about science and religion's relationship. Some argue they are incompatible because science assumes naturalism while religion assumes supernaturalism. Others claim they address different questions. Science explains how nature works, while religion addresses meaning and values. Einstein's position challenges both views. Against incompatibility, he shows that scientific practice can be religiously motivated if we define religion broadly enough. Against separation, he argues that cosmic structure itself has religious significance, not merely human meanings projected onto it. Modern physics has only deepened the mysteries that inspired Einstein's cosmic religiosity. The universe began in a Big Bang nearly 14 billion years ago and has been expanding ever since. Why does the universe exist rather than nothing? Why do physical constants have the precise values necessary for life? These anthropic questions revive ancient theological debates in cosmological form. Some physicists propose a multiverse, countless universes with different physical laws, so our life-permitting universe is not surprising, but statistically inevitable. Others see fine-tuning as evidence for design or purpose in nature. Einstein would likely have rejected both explanations, the multiverse as unfalsifiable speculation and design as anthropomorphic projection. But these debates continue the religious impulse to find ultimate explanation that Einstein embodied. Perhaps Einstein's deepest religious conviction was that the universe should be rationally comprehensible. He could not prove this. Indeed, quantum mechanics seemed to challenge it. But Einstein maintained this conviction as an article of faith, or more precisely, as the foundation of cosmic religiosity. Science rests on the faith that nature follows intelligible patterns discoverable by human reason. This raises a final question. Is Einstein's cosmic religion actually religious, or is it philosophy using religious vocabulary? The answer depends on how broadly we define religion. If religion requires supernatural belief, personal deity, worship practices, and moral commandments, then Einstein's views fall outside religion entirely. If religion encompasses any response to ultimate reality that evokes awe, reverence, and commitment to truth beyond self-interest, then Einstein was genuinely religious in his own way. Einstein himself thought the distinction mattered less than the underlying attitude. What mattered was cultivating the cosmic religious feeling, the sense of participating in something infinitely greater than ourselves, something both terrible and beautiful that demands our intellectual and moral seriousness. Whether we call this religion or philosophy, it motivated Einstein's scientific work and shaped his ethical commitments. It remains one expression, perhaps the most intellectually sophisticated expression, of humanity's perennial religious impulse to find meaning in confronting the cosmos.
The moment I noticed the switch in creativity and learning with my 3-year-old was really when I ordered a set of books.
Part 5, The Nature of Time, Block Universe, Arrow of Time, and the Present Moment.